This is a continuation of yesterday's lecture notes that we're finishing up. I'm thinking it'll probably take 20 minutes. Once upon a time, Isaac Newton came up with a thought experiment. And the experiment went something like this. Actually, are you guys familiar with Newton's thought experiment? He said where if you had a really tall cannon.
No. They had cannons back then?
If you had a cannon that was up on top of the world's tallest mountain, and you shot the cannon, what would the cannonball do? Do you guys know this, what I'm talking about?
No.
Oh, wow. So you guys never learned circular motion or gravity?
I guess not.
All right, so we got to do a quick review. This isn't in the notes, but it should be. It should have been in your notes last year. All right, so here we go. So Newton, once upon a time, one of his major thought experiments was this. Newton knew the world was round. And he said, what if you went to the top of the world's tallest mountains and put a cannon up there? And you fired that cannon, what would the cannonball do?
Which way are you firing it? Up or straight?
Sideways.
It should go over here.
It should fall, right? Right? Now, what if you shot the cannon faster? What will the cannonball do?
It would fall way farther.
It would go farther, right? What if you shot the cannonball fast enough?
Then you'd hit the cannon.
Would it still fall?
You would orbit.
Of course it would fall. It would fall
Go into orbit.
all the way around.
Yeah, but
All the way around. But why does it never hit the ground?
There's no ground underneath to catch it.
Well, the ground is curving away just as fast as the ball is falling. And so it never hits the ground. Does that make sense? So that was Newton's explanation as to why you should be able to orbit a planet. And think of when Newton was alive. Did they have rockets? No. They had cannons. They could shoot stuff. But that was about it. Does that make sense? So Newton predicted that you ought to be able to orbit a planet or orbit Earth if you could shoot something fast enough. Kind of cool, right?
Yeah.
You shoot too fast.
Yeah, so what if you shot too fast? Well, you go into that weird ellipse and you get a kind of an elliptical orbit. But if you shot fast enough, what would happen?
Circular. Yeah, circular.
You,
You had a circular orbit.
Oh, you had a circular.
if you shoot fast enough, it's just going to leave and go out in a hyperbola and never come back. Does that make sense? All right, so that was one of Newton's thought experiments. And that was the one that's kind of the foundation for orbital motion. It's his explanation of why orbital motion works. We talked about orbital motion already. I apologize for not bringing this one up earlier, but this is kind of how he thought about things. But he had a different thought experiment that's totally unrelated to this. And the different thought experiment went like this. You know that objects are attracted to each other because of gravity, right?
Yeah.
And if I had a rock, and I held the rock up, and then I let the rock go, it falls.
Yes. Agreed.
Why?
It's more attracted to the ground than you.
What's it being attracted to? What is the object that this rock is being attracted to?
The ground.
Mass
The-
of the Earth.
The Earth itself, right?
Yeah.
So what if you drilled a hole all the way through the Earth? All the way to the other side. Not just to the center, but entirely through to the other side, and you let the rock go. What would the rock do?
Wouldn't it
Would
hover
it hover
somewhere
at
near
the
the
center?
middle?
Go back and forth. Yeah, back and
Didn't we do this last year?
But
And
it
it hovers somewhere.
Then if you threw it harder, then it would come out the other side.
Okay, so law of conservation of energy, assume that there's no air drag to worry about, there's no friction, it never hits the side, because what would the rock do?
Continue.
It would go through the center of the Earth, and then
Harmonic motion.
Come back.
go out the other side, and then fall back up the other way, and come back into your hand eventually, right?
Yeah.
So it'll go in some sort of harmonic motion, starting one end of Earth, all the way through the middle down to the other end, all the way through the middle and then back to where it started, right? Assuming it didn't lose any energy?
Yeah.
So the question I have for you is it simple harmonic motion?
You'd have to prove this in the
Yeah, it is a restoring force. Gravity is pulling it always toward the center, but is the restoring force linear? And that's what we're going to talk about today. If you are inside a planet, what is the force of gravity when you're right in the middle?
0.
Isn't like undefined because it's 0 on the bottom?
Yeah.
You wanted me to draw a picture to help?
Yeah.
But GMM over it.
R would give you an undefined.
Yeah, that would give you an undefined value, a really, really big value. GMM over R squared says that gravity should be approaching infinity as R approaches 0, right? Is that what happens? Like, if you're sitting right here in the center, if you're sitting just barely away from the center of the planet, and here's your hole that you drilled all the way through. Here's the center, and you're just barely to the right of center.
Yeah.
Would there be a really big force on you or a really small force on you?
If you're less than yeah, really big.
Who says the force of gravity is going to be huge when you're right next to the center? Raise your hand. Who says the force of gravity is going to be almost 0 when you're right just barely to the right of center? Okay, let's argue it. Go, amongst your tables, come up with a decision.
Acceleration.
All right, let's take a vote.
Well, the gravity's
Now that
causing
you've had a
constant
chance to
acceleration.
discuss a little bit, who says the gravity, if you're just barely slightly off center, is going to be very, very strong? It's going to be almost infinity. Raise your hand.
We didn't reach a conclusion, so.
But I
Okay,
brought them over to the
Shrino,
dark
why
side.
would you go that route? Why would you say that?
You brought us to the side of, I don't know.
Wait, okay. shh.
You're welcome.
The equation says GMM over R squared, so if R gets really, really small, force should get really, really big, right?
Some crazy
Yeah.
stuff's going on with the masses.
But is there any counterpoint? Who says the force should be really, really small?
That's not what
Yeah.
you said either.
Because the mass is
Say that you go
smaller
in all
as you're going
directions,
in
so you can-
because
But
you're
it's
taking
small if
the
you're off
gravity at that point
It's
of
0
the
when you're
sphere.
in the
Oh.
center.
Not taking it at like the whole sphere.
Have you read
What
the
did he
notes
say?
already?
No, I haven't.
What'd you
Oh my God.
Did he say what I
He
said?
just jumped to the
I was thinking
complete right answer,
Because it's like moment
but he doesn't know why.
What did he
Does
say?
anyone have a different explanation for why the force should be very small? Blake, go.
Gravity is
Because
not
it's like a little bit to the right.
like the range of gravity.
You have all the mass from the left pulling on it, but you also have all the mass from the right pulling on it.
Okay, so you're saying if the rock is right here, just barely off center, how much of the mass is pulling to the left?
A little bit more than the right.
This much is pulling to the left. How much is pulling to the right? This much is pulling to the right.
See that?
Oh.
So when you're right in the middle,
That's a better explanation.
when you're right in the middle, what's true about the pull to the left and the pull to the right? They cancel. If you're just barely off of the middle, the pull to the left is a little bit bigger than the pull to the right. Does that make
I was
sense?
thinking circles.
Okay, now, James, you just skipped to the complete explanation that I was about to derive. All right. James's explanation is the one that we're going to end up with here in about 20 minutes. All right? But Blake's explanation I love because it's so easy to understand. All right, you guys got it? All right, so here we go. Thought experiment. Once upon a time, Newton had the thought experiment. If you fall through the planet, what would be the motion? Well, would it be simple harmonic motion? It turns out the answer is yes. It is simple harmonic. Now remember, in order to be simple harmonic, there must be not just a restoring force, but a linear restoring force, which means in the center the force has to be 0. And the further you go out, the bigger the force has to get, but it has to be linear. So if you double the distance from the center, the force needs to double too. All right? And we are going to prove today that that restoring force is linear. And in your homework, I believe tonight, you're going to have to figure out what the period, or in other words, if you dropped a rock, how long would it take to get to the center of the Earth? All right? Because that would be 1/4 of the period, right? If you could figure out the whole period, it's 1, 2, 3, 4. Take the whole period, divide by 4, it would be the amount of time it takes to get from here to the center. Sound good? All right, so here we go. All right. First, let's disregard this question entirely and just remember what the force would look like outside the planet. Now, outside the planet, what does the force do, Shrina? What's the equation? GML over R squared, right? Outside the planet. So in other words, outside the planet, if you're to make a graph of force, I made it negative just so it's clear that the force is always backward, right? So if you go this way, the force is negative. So outside, you start off with some value, and if you double the distance, you have 1/4 of the force. Agree? So from here to here, you get 1/4 of the force. But what I want to know is what's happening from the center of the planet to the surface of the planet. Is it a straight line? Yes or no? Is it linear? Well, if it's simple harmonic, it's got to be linear. So we're going to prove that it is. So at the center, the force is 0. At the outside, the force is not 0. So we need to know what happens in between the center and the outside. Is it linear? All right, here we go. Step 1. This kind of goes to Blake's explanation. Let's say you had a perfectly hollow sphere. Actually, I think, anyone ever read Hitchhiker's Guide to the Galaxy?
Yeah.
Remember, there's a part in the book where there's these people that make planets?
Yeah.
And they made Earth? And how do they make planets, you remember? They have a really big planet that they build the smaller planet inside.
It goes extinct or something because it does too much.
Right, so if Earth were entirely hollow, and all of its mass were concentrated on a shell, and you were standing on the surface of the Earth, could you tell that Earth was hollow?
Not unless you dug for it.
No, because you'd just be walking along, it'd just be just like Earth was Earth, right? But if there was a hole, like a manhole, to get to the inside of Earth, what would happen when you stepped over that manhole? Would you fall? Yeah, you'd fall in just like normal, right? Because so what would gravity be like on the inside?
It'd track you outside. Like you'd be upside down-ish.
So the instant you got just barely inside this hollow shell of Earth, what would happen? You fall in, but let's say you climbed in down a ladder and now you're on the inside.
Once you're
Would you fall to the center?
No.
Or would you fall to the outer surface? Who says, okay, let's draw a different picture. Here's hollow Earth. Ready? Hollow Earth. Hollow Earth looks like this. Here's the planet. Here's the hole. You step inside the hole. Now you're right here. Do you fall toward the center? Or do you fall towards the outside? Which direction would you be pulled? No, you start here at rest. Do you fall towards the center, or do you... In other words, are you being pulled stronger towards the center or away from the center?
Is it? Is it equal? Because isn't it more mass?
You would start
There's more
like
mass
orbit,
towards the
but there's
center.
greater, like less distance.
Yes! Did you hear it? Hey, over here too. Same explanation. What was the explanation? Go.
Because on that side, if you're going towards the center, there's more mass pulling you towards there, but on the other side, there's less distance, so the force would cancel.
Okay, so in other words, if I were right here inside this hollow planet and I looked this way, I would see all of this mass pulling on me. Agree?
Yes.
But what's true about all that mass?
Far away.
It's far away. Whereas if I look this direction, let's assume that was actually not a hole. I would only see a little bit of mass pulling on me, but it's close to you. So which one wins? The big mass far away or the small mass that's closer? Who pulls harder?
They cancel out.
They perfectly cancel each other out. Why?
Oh, that'd be cool though, huh?
Why? You would just, the second you got inside Hollow Planet, there is no more gravity. Or at least there's no net force due to gravity.
Wait, is it equal at all points or is it equal at a certain distance?
It is if you have a perfectly hollow planet
Yeah. It'd be freaking cool.
and you're on the inside of the hollow planet just floating, you would just float. You wouldn't fall in any particular direction. Because the majority of the mass is farther away, right? Because if you look one direction, you see a lot of mass, but it's far away. And if you look the other direction, you see a little bit of mass, but it's closer. And the reason they perfectly cancel out is because if you look at the equation, the force depends on radius squared, right? So if you double the distance away, that means you get 1/4 the force. But if you look at a given angle, it'll sweep out a certain area, right? So if you double the distance away, it'll do 4 times the area with 1/4 the force. 4 divided by 4, they cancel. The two effects cancel out perfectly.
Would this apply at any point in the planet?
Any point inside the planet, inside the hollow planet, yes.
If you like jump in, will you just smash all the way to the bottom?
Yeah. So we know if you're on the outside, it acts just like normal Earth was, and you'd fall towards Earth. But if you're on the inside, there is no gravity. So what would happen if you had a little manhole and you jumped into the manhole?
You'd keep going in velocity all the way.
You'd keep on going with a constant velocity until you impacted
The other side.
the other side.
At least you wouldn't be falling that fast.
You'd probably starve before you hit the other side.
Right. Oh, I don't know. That's your homework tonight is to figure out how long process would take.
It's pretty freaking cool.
You didn't see Ender's Game, did you?
I did not see Ender's Game.
Did you read the book?
I did. Years ago, though. It's been a while. I need to read it. It's sitting on my bookshelf, waiting to be read again.
As like the spinning space station.
Yeah.
We talked about where it's more massive to the outside.
All right. So, do you guys got this? All right. So, step 1 of this proof, proving a linear restoring force goes like this. If you have a hollow planet, there is no gravity effect from that hollow planet. Now, what that means is any mass, guys, this is the important part. Any mass that is outside your current radius provides no net force on you. Should I say that again? If you're at a radius of 1,000 miles from the center, and all the mass is at a radius of 2,000 miles from the center, in other words, it's at a greater radius than you are, any mass that is a greater radius than you're at right now will not pull on you. Or at least it provides no net force on you. Does that make sense? As long as it's a complete shell. Now, if it's only half a shell, obviously you're going to be pulled in one direction. But if it's a complete shell that entirely surrounds you, any mass that's outside of your current radius doesn't pull on you.
So if there's like a, say, a city built on the other side of it, you were like,
Inside
would
the
you, yeah, would you be pulled toward the city or? If
You gotta assume an even mass distribution too.
Okay.
Yeah. All right, next. Whatever sphere or portion of the sphere that you happen to be standing inside of that you happen to be standing inside of will not provide a net force on you. Step 2. Now let's figure out how much the portion of the spherical planet that is inside your current distance is pulling on you. So we're back to a solid sphere again. Let's say that we were halfway to the center. The center is at the center here. We are halfway to the center. We know that if we draw a circle or we draw a sphere, any of this mass out here is outside of us, right?
Yes.
Can't pull on us. Or at least doesn't provide any net force on us by the hollow planet explanation. Do you follow that? Which means the only stuff that matters is the stuff that is inside our current radius. Which means as you fall, the planet is effectively getting smaller. Or at least the portion of the planet that's pulling on you is getting smaller. Does that make sense?
What happens when you're at the center then?
How big is the effective planet that's pulling on you?
0.
Size 0.
Oh, okay.
All right, and this goes back to James's explanation. All right, so the force on you when you're at a distance of x from the center is going to be gmm over x squared. One of those m's is your mass, which isn't changing, but one of those masses is the mass of the effective planet size. That's got a radius. Now, in order to figure out that mass, you need to know the volume times the density, right?
Yes.
Let's assume that the density of the planet's constant. It's not, but it's pretty close. What's happening to the volume as you get closer? It gets smaller. Do you guys remember the equation for volume of a sphere? 4/3 pi r cubed. That's key. Pi r cubed, because it's 3 dimensions, not 2. Do you guys know that about radius? Okay. All right. So the force is gmm over x squared, but the mass is proportional to the velocity, which is 4/3 pi r cubed, which means the volume, sorry, which means the mass is proportional to x cubed. So the force is proportional to the mass over x squared, which means that the force is proportional to x cubed over x squared, which means the force is proportional to what? X. Force is proportional to distance from the middle. Does that sound familiar? That means it's linear, which means if you go from half of the radius to the full radius, it's a factor of 2. So if you weigh 160 pounds now, how much are you going to weigh when you're halfway to the middle? 80 pounds. Does that make sense?
So you're effectively losing mass.
You are losing weight. You're not losing mass. You're losing weight as you fall. So good weight loss plan, right?
Yeah.
Dig a really big hole
Well, that's nice.
and just go crawl down it.
Can you imagine? Hey, I'm like
Hey,
50 pounds
wrestlers
lighter
can
now,
be in
so
their new
suck.
weight class.
Yeah, there you go. So your homework tonight is to go through this derivation and figure out how long it would take to fall to the center of the planet. And this is one big put it all together for the whole semester problem. All right, you got simple harmonic motion, you've got some math involved, you've got some forces involved, you got some gravity involved. All right, and that's it. That's all I have.